Good morning.
Good morning, Trevin. Good morning, Matthew. How are you guys doing?
Pretty good. How are you?
I'm hanging in there. Almost done with this semester, but then my summer will start pretty soon. I don't know when it starts. I'll be teaching a Chem 8 in summer, so no break for me for some time. Then maybe after that I'll have some fun. Hey, Michael. Good morning, Ray. Good morning, Henry. I need better coffee. Hey, Dilshan. Man, another semester is gone. It's like it's sitting in a train. You guys don't know what train is, right? How many of you have ridden a train in this country? You have ridden a train, Michael, in US or in Europe or in Asia?
Yeah, I've ridden Amtrak before.
Okay. Yeah. Train is kind of fun. I like trains. I like train more than airplanes. Airplane is fun too. Planes are fun. I actually like watching planes take off and land more than being inside. Hi, Vanessa.
Hi, good morning.
Good morning. How are you?
Good, tired.
Tired. Yeah, I know everybody's tired. Yeah, well, not everybody is tired, but most of us are kind of tired. I was supposed to submit a grant by May. I just don't have the luxury to spare time. I haven't been able to even review the reviewers' comments from the past grant submission. I don't know what I'm doing, but then it seems like there's no end of chores. It's almost 8 o'clock. I think the attendance is pretty clean today. Only 5 of you or 7 of you. 1, 2, 3, 4, 5, 6, 7. Where is the rest of you? Rest of the
I think people might be getting ready for registration, to be honest.
Oh,
Yeah.
registration for
For next semester, for fall semester?
what semester is this? This is spring.
This is spring, yeah.
Okay. Yeah, I need to like really set my clock sometimes. All right, Daniel is coming in, Edgar is coming in. I'll wait for a few minutes because today I think I'm going to finish substitution, talk about some elimination reactions, and might get the ball rolling in the court of Carbonyl Garden. Hey, Carly. Hi, Desiree. Desiree's coming in. How are you guys doing? Let me just try to remain quiet and hear you out. Anybody has anything to say? Hi, Greg. Hi, Craig.
Morning.
Morning. How's life for everyone?
Another day. All good.
All good. Sounds good. Hi, Marco. Hi, Queenie. Desiree has that bulldog. What did you say? Sorry.
I said good morning.
Good morning, Queenie. Any comments? Any opinion about anything? Doesn't have to be organic chemistry. Hi, Willis.
Hey.
How come Willis shows up on the top of my screen all the time? And his last name and first name start with W, so there is no priority for him. How come he's on the top of the screen? That's not fair.
I don't know.
He's not even drinking coffee, and he's getting priority. Hi, Lupita. Hi, Karina with a K. Hi, Roberto. Hi, Fernando. Hi, Julissa. How come I missed you guys?
Good morning.
Hi, Isaura. I probably butchered that name. How do you say it? Isaura? Isaura?
Isaura.
Okay, sorry. My bad. All right, let's go to the board. Hi, Danielle. Phillips connecting. Lupita, I think I said hi. All right. We are recording. So the plan for today is talk about a little more, just go through some examples of substitution reactions, show you like what happens to primary, secondary, and tertiary. I'm going to leave out some of the really fine details of this chemistry. You don't need that. I don't really know how many of you are going to be using this material. So we're going to go over that, talk about something like, what can happen under special circumstances. And we'll talk about that a little bit. And then we will, if we have time, again, you know my history, how it happens, how things go a little slower than usual. And if we can, maybe just introduce you to the world of carbonyl molecules. Okay. Let me switch to the board. I think it looks fine. Nothing funny has happened in the world of Zoom. Okay, let's go. No more, no more introduction is necessary. Seems like a nice day. Pretty peaceful. Everything looks peaceful. Hopefully, the world will go peacefully today, wherever there is day. All right, people in India are getting COVID-19 infections like crazy. Some of our friends are sick now, but I think it looks like the mortality rate is pretty low. So, but it's a very infectious strain that's going on in India. So our friend, the whole family, husband, wife, and their 15-year-old daughter, they're sick. My wife's friends are sick. So it's pretty out of control. I think Brazil and India are really messed up right now. US seems to be doing much better. All right, with that, let's get started. So we are Chem8, and today is April, I have no idea, 22nd? Yes, 22nd. April 22nd, I know, I should have known because tomorrow is some deadlines for me, like some evaluations for my fellow colleagues. I have to finish that. And we are talking about substitution reactions. Okay. All right. One more time, a reminder that we will have a review, pre-final review on 6th, which is 22nd, 2 weeks from today. Same time, we're going to start at 8. It's going to probably go a little longer than usual class. It's probably going to go for like a couple of hours. And we'll try to just go over some quiz and exam test questions and have you guys kind of solve it. Or I'll just go over the materials from my mind, unless you have a question, put up some problems and have you guys solve it. I don't have any plans to record that review session. Okay. So let's very quickly, let's do a little review on the right side column. Okay. So when we have Rx alkyl halide, bromoalkane, okay, chloroalkane, chloromethyl, chloroethane, bromobutane, well, 1 bromobutane, 2 bromobutanes, and things like that. So you have these molecules, and that's a good living group, the X guy, the halogen, and it can react with a nucleophile. Okay. It can react with a nucleophile, and it can do a one-step reaction and attack from the backside. You know what? Let me just make sure that it looks like the backside. Okay. So wherever in the alkyl halide, wherever the halogen is, that's the front side. Let me just write that down. This is no, not that color. Confusing. This is front and this is back. Okay. So the nucleophile comes in from the back side, kicks out the living group. That's the living group, and you have a new product. Okay. So let me write this guy a little bit closer so that I have the room on the other side. Okay, so this plus this gives you nucleophile attached to whatever the alkyl part is, carbon hydrogen part is, it's that, and X is out. And this is a substitution reaction. You are substituting something with something else. That something else happens to be the nucleophile, and that something happens to be the halogen. Okay, the halogen is happy getting out because that anion is kind of spreading its negative charge over that surface. Fluoride is small. Remember, chloride is a little bit bigger. Bromine minus is a little bit bigger, and iodine minus is really huge. So it's tiny, a little bit bigger, really huge, right? So iodine minus, remember, iodine minus is the best living group. F minus, comparatively, and on a relative scale, is the worst living group among the four. Okay, so this pathway is known as, this is step one step only. Okay, step one, and this is called Sn2, substitution nucleophilic. 2 stands for bimolecular. It has nothing to do with the number of steps. Okay, it's one step, but it's Sn2. It's opposite to your instinct. Don't connect the wrong dots. Okay, in the exam or in the quiz. Why is it called bimolecular? Because in this step, in this only step, that step that basically determines the fate of the reaction, how fast or how slow that reaction is going to go, it's often called rate determining step, but you don't have to memorize that. It's not within the, let's say I'm not going to ask you about it. Okay. 2 means bimolecular because both molecules are involved in the important step. Got it? That's why it's called bimolecular. In the second mechanism, not Sn2, what happens instead is the nucleophile is not in the picture. All that happens is the living group leaves, creating a hole, creating a carbocation hole. That's all that happens. And this is step 1. Step 1, and this happens to be the slow step. Slow step is the step that determines the fate or the rate of the reaction, like how long it's going to take you to come from Reno to Fresno. Reno is about 4,500 feet, and Fresno, let's say 500 feet, right? But when you come from Reno to Fresno, you climb over Donner Pass. So you climb over Donner Pass, and that's the hardest, that's the longest time it takes you to get through. It's not entirely true, but just use this metaphor, okay? So you climb over Donner Pass and you come down to some point like 4,500 to 7,500, then you roll down to, let's say, 5,500 and get to, I don't know, Nevada City, and you stop there for some time. So step 1 is done, and you, let's say you took like 4 hours to do that. It doesn't take 4 hours, but just for the sake of argument. 4 hours to get from Reno over Donner Pass to Virginia City. Step 2 starts from Virginia City, a little hill, and then you climb back down to Fresno. Let's say it takes you 15 minutes. That's not how it happens, I understand. But for the sake of the reaction, let's say that's how it happens. So the second step is fast. First step is slow. So the first step is called the rate determining step or the slow step. That, let's remember it as the important step. Okay. So this is important. That's first step is important. What happens in the first step? Well, this is what happens. You form a carbocation. Okay. You form a carbocation, and that guy is out. Oops, wrong color. Halogen is out. The living group is out. It has detached itself. Now, in the second step, this is step 2. step 2, and this is fast. This step is fast and not so important as far as the fate of the reaction is concerned. The big deal is, this is the big deal step, okay? And in this state, the nucleophile comes in. It can either attack from the front. I don't know what it looks like. It can either attack from the front, or it can attack from the back. Okay, it's relevant and it's important when that R is when this guy is chiral. I'm not going to get you guys into that discussion. I'm going to spare you from the discussion. If you come back to Chem 128A, which has happened in the past, in my current 128A, I have a student who had taken Chem 8 from me in the past. I don't know what the deal is, how it works out, why she's doing that, but she's actually a good student. So she's learning all this stuff. So front and back attack can happen, and you can have the nucleophile attaching itself from the back side of R. This means nothing because it's 2-dimensional, right? It really doesn't mean anything, but kind of like, with that cartoon diagram with R on the right and nucleophile on the left, it kind of gives you an impression that it's attacked from the back. This guy happens, and this guy happens too. The back side, the front side attack. Okay. It doesn't make any sense in most cases, but if this is chiral, if R has that alpha carbon is attached to 4 different things, including the halogen, then this can be a big deal. Okay, so usually you get 50% of this and 50% of the other one. Okay, and this 2-step procedure is called Sn2. I misspoke. Not Sn2, Sn1. Okay, that's Sn1. Let's talk about some bullet points. I'm not going to write them down. Okay, let's say, give me a bullet point for Sn2. Say something about Sn2, which we have. You can look in your old notes or the video or this picture. Somebody say something. Don't use the chat or give me any gesture because I'm not really looking at that screen. Okay, something about Sn2. How many steps?
1 step.
1 step. Somebody else say that corresponding comment for the Sn1 reaction. How many steps is Sn1? Somebody else, not Michael.
2 steps.
2 steps. Okay. Something happens in Sn1 that doesn't happen in Sn2. What is that? Something forms in Sn1 that something doesn't form in Sn2.
Carbocation.
Carbocation happens in Sn1 or 2?
Sn1.
Sn1. Okay, great. Somebody else say something about how the nucleophile behaves. Not those who have already spoken. How does the nucleophile attack in Sn2 and how does the nucleophile attack in Sn1?
I'll answer that. SN1, the nucleophile attacks from front and back.
And here?
That one attacks only from back.
Awesome. Great. Thank you, Ray.
Well, I was reading the notes, so.
Yeah, perfect. Let me ask you something that I missed on Tuesday. Between fluorine, chlorine, bromine, and iodine, okay? If you have, you know what? Let that be a problem. Maybe we'll start our next set of discussions with that, and I'll test your knowledge. Something else you're missing? What else? What else can we say? What else have we learned about the reactions? Okay, yeah, important. What kind of alkyl halides like that way, and what kind of alkyl halides like this way? What kind of alkyl halides are preferred by Sn2 mechanism? Primary, secondary, tertiary.
Primary.
What kind of alkyl halides? Somebody else. What kind of alkyl halides prefer to do Sn1? Someone who hasn't spoken today. It should be the other end of the spectrum.
Tertiary, right?
Tertiary, right? Yes, Julissa, thank you. Okay. Can someone who hasn't spoken today explain why tertiary alkyl halides like to do this business, two-step reaction? Somebody who hasn't spoken today. Why does tertiary like going the two-step mechanism? What's so special about them? Think, connect the dots, wake up. Wake up, we have to go. We have to go to the intermediate, we have to make the carbocation. What if your mom wakes you up in your one day and says, we have to get to that intermediate state, wake up. We have a long way to go, step one is starting right now. That could be a nightmare, man. Or
Is it
lady.
because
Yeah, because Fernando, yes, go ahead, sorry.
tertiary is more stable?
Tertiary, what is more stable? Tertiary alkyl halides or tertiary something else?
I don't remember. In my notes, I just have it as tertiary.
Tertiary what? Somebody else pitch in. Anybody?
It's the density of electrons.
The carbocation is.
Carbocation, yes.
Yeah.
I was looking for that. I was looking forward to hearing that word, carbocation. Tertiary carbocations are stable, right? Everybody put things together. Finally, it's going to happen sometime soon. Don't screw it up, please. I want you guys to do well. I'm going to keep the final really straightforward, nothing tricky. I want all of you guys to do well. Please don't get demotivated. Beg, borrow something with your supervisor at work and try to sneak out. Say your left front tire had a flat, then you can come up with, you have 4 tires to go through in a week. Remember that, unless you ride a motorcycle or a unicycle. Then that's a different story. You have only one tire to come up with an excuse for. Oh, I ride a unicycle, I had a flat tire, so I couldn't come to work. I actually bought a unicycle at the beginning of the pandemic. I haven't taken it out of I need to learn how to ride it. It's going to be a lot of fun and maybe some broken bones. Okay, so tertiary likes doing this, primary likes doing that. Why? Because primaries are really terrible about making a carbocation. For reasons you should know, we have discussed it more than once. I expect you to know that. Okay, the help from the neighboring alkyl groups, they are pumping electrons into the carbocation center. If the carbocation center is getting some assistance from the neighboring groups, pumping electrons through the bonds toward that carbocation center, they feel good, right? So primaries cannot make carbocation, therefore they do this. That's the only choice they have. Otherwise, the reaction is just not going to happen. Okay, all right. So think about it for a second, whatever we have discussed. So this is going to be in a box. This is on the side. How straight is my straight line? Absolutely not straight. Terrible straight line. Whatever. I'm not going to fuss about it. I'm already fussing about it. Okay. Take a look at it for 15 seconds, then I'm going to throw some example and ask you a question. No points attached. One step, two step, carbocation, no carbocation, primary alkyl halides like doing that, tertiary alkyl halides like doing this, two step, one step, only backside attack, front and backside attack because the carbocation is flat. What else? Yeah, something like that. So, all good? So far, so good? Okay. Let me ask you a question. Let me set up. This is something you might see in the quiz. Okay. All right. Four birds, four migratory birds, they're flying. They don't fly that way. They fly pretty much at the same elevation. They take their positions to switch in the front. The leader, position is changed. I hope you, I don't know if you know that, because they get tired. It's kind of like following a big rig on the freeway. If you're really running low on your gas, I have never done it. So you can actually follow a big rig and you can use its, the wind, and your gas mileage goes up. Don't ask me how I know. Chlorine, bromine, and iodine. Okay. Okay, let's practice my favorite thing in organic chemistry, nomenclature. How would you call that guy? Somebody who hasn't spoken today. So I'm forbidding everybody who has spoken today, starting with Michael, Ray, Fernando, Craig. Who else has spoken today? Julissa spoke today. Yeah, those of you who have spoken today, try to control yourself. What's the name of that guy? CH3CH2F. Hurry up, quick. It's already 8:20.
Is it fluoroethane?
Fluoroethane. Danielle, 4 out of 4. What's the name of that? Let's practice. Somebody else who hasn't spoken today. Danielle, you are forbidden. Somebody else. What's the name of that? That's fluoroethane. So figure it out. It's easy. Somebody has already laid the path. What's this guy called?
Fluoroethane.
Fluoroethane. Vanessa, awesome. Somebody else tell me what the name of this molecule is.
Bromoethane.
Thank you, Peyton. What's the name of this? Iodine with an ethyl group. Somebody else. Iodine becomes what when it's a branch? Iodo. So now put the things together. Somebody.
Iodoethane.
Iodoethane. Perfect, Roberto. Fantastic. Fluoroethane, chloroethane, bromoethane, iodoethane. We don't have to specify one or two because it doesn't matter. It's always going to be one, whether you put the fluorine on the right or left. Right? Got it? Okay. But if the chain becomes bigger, more than 2 carbons, then you have to specify 1 fluoroethane, 2 fluoroethane, something like that. 1 fluoropropane, 2 fluoropropane. All right. You know what's going to happen now? They're going to undergo reaction. And this is reaction 1, reaction 2, reaction 3, reaction 4. They're all reacting with sodium hydroxide. They're all reacting with sodium hydroxide. Let's put that hydroxide in a different color. The color I haven't used it yet. OH minus, OH minus. Okay. And what's going to happen? Well, they're going to come from the backside. In each reaction, this is what's going to happen. That's going to get kicked out. This is going to get kicked out. This is going to get kicked out, and this is going to get kicked out. Okay. And as a result, every reaction is going to produce the same product. I don't need this pen anymore. Oh no, I do need the pen. And then we have F minus, Cl minus as a byproduct, Br minus, and iodine minus. Who can predict what I'm going to ask? Anybody? Who can, what is going to be my question after writing down all this stuff? What's going to be my question? Who can predict that? 4 reactions, 4 halogens, pretty much the same alkyl group and same product. We are making alcohol. 4 students are making ethanol, our favorite alcohol, in 4 different ways, starting from 4 different starting materials. What will I ask? Any prediction? Who can read my mind? No wild guess.
What kind of reaction is it?
Yeah, I can ask that. I mean, probably I'll start asking about that. What kind of reaction is it? Is it Sn1 or Sn2? Blah, 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 blah. Which one is the living group? What is the nucleophile? Okay, but what's going to be the significant question I can ask? Why am I putting these 4 different alkyl halides? What's the significance of that? Can you stretch your imagination a little bit more and try to be a astrologist and read my mind? We can start a side business. We can predict future for people and ask them to pay us like $5 for predicting future. I think that's a pretty good profession. I might change it. What's the important one? Why 4 different alkyl halides? Anybody wants to take a wild guess? No? Okay. No? All right, my question is, there are 4 reactions going on. Alkyl halide, so ethyl, fluoride, chloride, bromide, and iodide, right? They're living groups. So this guy is a tiny guy with a negative charge. This is a little bit bigger with a negative charge. Bromine is a little bit bigger with a negative charge. And iodine is even bigger with a negative charge. Okay. My question is, ready? Which of the 4 reactions will be the fastest reaction? If you have a choice of using any of the 4 reagents, and it's your boss, let's say I'm asking you to work on a Friday afternoon, you have a game to attend at 5 o'clock, and it's already like past 1 o'clock, and you're like, man, I hate this instructor. I don't know why Shantanu is asking me to make alcohol Friday afternoon. I have to go. So I'm going to, and he didn't specify how I make it. And on the shelf, we have fluoroethane, we have chloroethane, bromoethane, and iodoethane. Which one would you use to get out of the lab fastest? Which of the 4 reactions will go fastest and why? Justify. Anybody can answer.
Would it be the first one? Or,
You cannot ask, you have to answer. Which one is the fastest? Okay, so Vanessa, did you answer? Did you say number 1 reaction?
yes.
Okay, so Vanessa thinks it's this. Anybody else?
I
I'll
think
do
it's
it.
the 4th one because iodine is
Don't
the-
know because yet. Hold on. Craig thinks it's this. Anybody else? Somebody else was trying to say something.
I would say it was fluorine too.
Okay. Danielle, you think it's the first one or the fourth one?
The first one.
Okay. Daniel thinks it's the first one. Anybody else?
I'll agree with Craig that it's the fourth one.
Okay. So okay. Good. Very good. Okay. Ray thinks it's VD and CR. Anybody else? Let's pick one more person so that if we can have 2 to 3 or 3 to 2 voting. Somebody else.
Battle of the Sexes. Let's go 4.
Not William, it's Michael. What shape do you want, Michael? We have square, circle. How about a wiggly line?
Yeah, that's unique.
Yeah, that goes well with your beard. Okay. All right. Vanessa or Danielle? Why do you think anybody wants to? No, I want to hear what were you thinking about why it is 1? What's
I
the
was
justice?
think-
Yeah,
I
go
was
ahead.
thinking of the electronegativity, but I'm kind of thinking like if it's I or iodine, I'm thinking maybe it has to do with the atomic number.
I was thinking it was
Those-
least stable.
Sorry,
I was thinking it was least stable.
least
that's
stable. Okay, so think about 2 houses. Your house and your neighbor's house. In your house lives Vanessa as the only child of the parents. And in your neighbor's house, it's Danielle, who is the only child in the neighbor's house, right? And both set of parents are trying to get a paying guest. Okay, I'm using you guys as an example. Don't feel, offended or anything. Okay, just an arbitrary example. Let's say 2 houses, there are 2 daughters. Okay, one starts with V and one starts with D. Okay, one of them, one of the 2 daughters is more happy or stable as an independent person. Okay, iodine is a bigger sphere with a negative charge. F minus is a smaller sphere with a negative charge. Okay, which one is more stable, more happy? Iodine minus than fluorine minus. If that's the case, if you're producing something, if one person is going to be out of the house here in this house, and one person is going to be out of the house here in the other house, and this person is going to be more independent, more secured, more happy, more stable, less reactive, which house is more likely to create that opening? Which house is more likely to have that process happen when the paying guest comes in, the nucleophile comes in, and the living group leaves? Which one is more likely to happen when it's this is more stable? This is more stable versus less stable. Vanessa and Danielle, I'm not trying to put you on the spot. I'm not trying to make you feel bad. I want everyone to kind of get that logic. Can you guys see, like, you want to change your answer? You guys want to stick to your answer? What is going on in your mind? Can you think logically? This is producing something that's less stable than that. So is that going to be more likely to happen? Or is the 4th reaction going to be more likely to happen?
The 4th.
4th, right? So this is the wrong answer. So the right answer is reaction number 4, because it's producing something more stable. This is a concept that takes time to understand, to fathom, to kind of sync with your system. Because you haven't spent 30 years in doing chemistry and thinking chemistry like I did, right? So it's totally understandable. And some of you are not, chemistry is not your cup of tea. So there is no need to be apologetic or feel bad. I'm glad that you guys are participating. That means a lot to everyone. Okay. So when when the reaction, a chemical reaction, doesn't like to go forward if it is producing something unstable. Make sense? So a chemical reaction will happen between two reactions. The reaction that will happen more likely, more quickly, is where you are making something more stable, more comfortable, less reactive. If it is going to produce something that's not stable, it's not going to happen. Or on the relative scale, it's going to happen less. Is everyone following this concept, this concept and application of the concept? I'm going to pause for like 30 seconds. Let's see if I can do that.
I don't know if it'll help, but like there's an easy way that I kind of visualize the electronegativity and stability of lone atoms of like a like let's say two, like one, you know, like north side and one south side magnet are, you know, touching together, they'll attract together. But then because it's just one and one, it's decently easy to like tear them apart. But if like a whole bunch of magnets are put together, it would be proportionally harder to take one out, because the more positive and negative sides there are, the more they'll attract together, the more stable it'll be. That's kind of how I
That's totally
visualize
fine.
it.
Whatever works. You heard Michael, and if it goes well with your system, adopt that thinking pattern, adopt that logic. Anything that works until you are done with the final exam. Okay. This bond is also, this is the weakest bond. You know what? I'm not going to go there. I didn't say that. Okay. I don't want to bring in another angle and confuse you guys more. I'm going to say that stability of the iodide, the final product, the anion. But if Michael is talking about magnets and how they're attracting with more electronegative, attracting more strongly, if that syncs well with you, use that. Okay, so this reaction is going to be the fastest, and that's going to be the slowest. Okay, I think it's time for me to do some photography.
I have a question.
Yeah.
So if you ask the question, which one, like you said, which one's the fastest? We're gonna look at the size on this.
Yeah, you think about one of the two products. This product is the same, right? Like it's ethanol, right? There's constant in all four reactions. There's nothing that's discriminating the reactions one from another. What's different is the byproduct. The byproduct is a tiny little sphere, like a little glass bead with a negative charge. Over here, it's a tennis ball, golf ball with a negative charge, a tennis ball with a negative charge, and a big soccer ball with a negative charge. This guy, this soccer ball, is the happiest, most stable, right? So reaction one is producing something that's less stable. Reaction 4 is producing that's more stable. More stable, least stable. Which reaction is going to be happening more? That's the one that's producing something more stable, or a reaction that's producing less stable. That's how you need to connect the dots. Okay? Me and my brother, let's say me and my brother is more independent and more matured, less hyperactive. So I'm going to be much less likely to be getting the permission to go and live in an apartment than my brother, because my parents don't trust me, right? My brother is more stable. Iodine is like my brother, and this is like me, right? I'm hyperactive, I'm impulsive. So my parents don't trust me. They think that I'm, as an independent single person out in the society, I'm probably going to be more reactive. I'm going to screw up something, okay? My brother, on the other hand, is more trustworthy. That's how we grew up. And they still say that thing the same way. Doesn't change. Some things don't change with age, okay? So this is more stable, this is less stable. That means the fourth reaction is going to be more likely to happen. That means it's going to be faster, where nature is producing something more stable. if nature is producing something more stable versus nature is producing something less stable, the process that's producing something more stable will happen more. Simple logic. Make sense? Is it going well with your system, thinking style?
Yes.
Ray, are you comfortable with this concept?
I'm listening.
Sorry.
I'm going with it. That's why I asked the question. So like I said, if I saw this question on a test or the quiz and it said which one of these examples is the fastest and why, I'm gonna go because this was because the
More
iodine
stable.
is more stable.
Does anybody have any other metaphor that can help everybody kind of get this concept? Michael had some idea. Sometimes you guys have a better idea than I do. Seriously.
The way I conceptualize it is just I memorized how if you look at the periodic table and you have an arrow pointing to the right and pointing to up, that's the corner is going to be the most electronegative, and so it's going to want to attract to it to the most, and so that would just be fluorine. So that's how I think of it. It's not pretty stale, but it seems to work.
Craig and Michael have similar concepts, but they're kind of like using it in a slightly different way. So fluorine is most electronegative, right? Periodic table. I appreciate all of your inputs. If this is the periodic table, fluorine is here, right? And bromine is here. Fluorine, chlorine, bromine, iodine. Helium, neon, argon, krypton, xenon, right? The inert atom. Then over here we have nitrogen, phosphorus, blah, 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 arsenic. I forgot what they are right now. Carbon, silicon, and then we have boron, aluminum, etc., right? Then we have lithium, sodium, potassium, etc. So most electronegative, less electronegative, less electronegative, less electronegative. Electronegative means hunger for electrons. So you can think using Craig and Michael's concept that this bond, this guy is more electronegative than that. So this bond is more sticky. This bond is a little weaker. This bond is a little more weak. This bond is the weakest because it's least electronegative. Its love for the electrons is least. That means this bond is going to be the hardest to break. This bond is going to be the carbon iodine bond, which will be the easiest to break because iodine is not so greedy. Okay, you can more easily kick it out. That you can think about it that way too. Yeah, whatever works. Ray, that might help.
Okay, yeah, it does because electronegativity, it goes up and then to the right, correct? On the periodic table?
Electronegativity goes up, right, goes down this way.
Right.
When you go left to right, electronegativity goes up. Less, more, less, more, highest. As you go down, more, less, least.
Got it.
Because you're adding a shell, you're going further away from the sun. Okay, so the attraction gets low and your power to attract electrons gets less. So this way and this way, this is how the electronegativity increases. That looks like a really weird dance move. You can somebody who is really good with dancing, you can choreograph some things from using organic chemistry concepts. Okay, makes sense? Let's move to the next concept maybe. Okay, we have about half an hour left. Let's use it judiciously, as they used to say in my company. In the corporate world, people choose words very carefully. Sometimes here too, like HR administrators, they will use words very carefully. They will not write anything that's a little sketchy or borderline, whatever they can get into, they will not write it down in the email. So they used to use this word judiciously quite a bit. They will take a judicious decision. Once I asked for like a raise because I thought it was fair, and my boss said something that really made me angry because he gave me a textbook example, like, your request will be evaluated in due course of time and you will be notified, blah, 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 blah. And I was so mad, but I had to wear a plastic smile. And that's why I left the industry. So anyway, that was unrelated to what we're talking about. Okay. What I'm going to do is I'm going to erase the left side and put two other reactions and ask you which one will be Sn2 and which one will be Sn1. And then I'm going to introduce you to an elimination reaction. I'm not going to like spend too much time on that. We'll just introduce you like what can happen certain times when you have a reaction that you think will be substitution, but it goes the wrong way. It literally goes the wrong way sometimes. Okay, I'm going to keep everything on the right side pretty much the same way and just erase the left side. I really appreciate your participation, all of you guys who are participating, and I know that everybody else is absorbing like a sponge. I like this class always. I've said that. So it really makes my Zoom life a little more worth living. Okay. Otherwise, I'll be honest with you, I don't like it. I don't like virtual teaching. And I got scared. We have our faculty meeting yesterday, and there was again some discussion about whether fall is going to be in person or virtual. I'm like, I can't deal with this anymore. You know, I want in person. I'm done with virtual life. I think US is in much better shape than many other countries. And if we don't screw up anything big time, I'm a little nervous about California opening up on June 14th. I hope that not, like all hell doesn't break loose after that. I think if the vaccination is good, we should be fine. But I'm a little afraid that what if something goes wrong? What if a new strain comes in? And what if that doesn't get, you know, tamed by our vaccines right now? I'm a little nervous, but keeping my fingers crossed. I think it's time for us to be successful. My role of paper towels just, you know, separated cell division, and it had its twin brother. Okay, it's magical. One in the middle of the night, the cell division happened, and I have two now. It's awesome. It's pure magic. Weekly line is much easier to draw. See, this is why people don't go in the straight line when they want to be wishy-washy, because straight lines are very easy to distinguish. If it's either straight or not straight. But if you draw a wiggly line, that's how the corporate world works. They draw wiggly line. They don't draw a straight line, because what if my straight line is not straight? Then somebody will say, oh, Shantanu doesn't know how to talk straight. But if I go like beat around the bush, people will never say Shantanu is beating around the bush. They will say, huh, interesting. There are a bunch of different concepts here, different views, and we need to think about it. And then there will be another meeting to discuss what I said, right? Then there will be a third meeting to discuss what they discussed in the first meeting. So it's really good. All right, so let me ask you some questions. Let's say we have this, and let's use a nucleophile that we haven't used so far. Let's use a nucleophile, a nitrogen nucleophile. How about that? How does it work? Well, it comes and attacks. Chlorine gets kicked out. It first produces something like this. You know what? I'm going to keep your life easy, and I'm not going to do this. The pandemic special. This is going to be the pandemic special. Okay, let's use a different system. Let's use sodium epoxide. Okay, alcohol, ethanol, you pulled out the proton with sodium and it became sodium plus and O minus. So this is an awesome nucleophile, right? So I'm going to use, for your information for this course, I'm going to always use a negatively charged nucleophile. Because if I use a neutral nucleophile, I have to teach you one more thing. I don't want to teach you that, not because I don't want to teach you. I don't want to dump one more thing in your brain right now in your hard drive. Just let's keep it simple. Okay. So when this reaction happens, you're supposed to produce this molecule. All you do is think about it this way. If you have to just like predict the product, alkyl halide, that's your leaving group. What do you do when you have to draw the product? You erase the leaving group and you draw the nucleophile. That's it. You erase the leaving group, you remove that, and you plug in the nucleophile. That's how you need to think when you're just taking a test. Okay. So alkyl group, how many carbons? Don't screw up the number of carbons. 1, 2, and 3. So you make sure you are not dropping carbons or adding carbons. You got the 3 carbon chain, propyl group. You get rid of that. This is out. And this is out as a nucleophile, as a leaving group. Chlorine is out, right? And what's in? That dude is in. That's your brand new paying guest, right? You attach the paying guest. How do you do it? Sorry, I didn't plan it very well. And Cl minus. Okay, so that's your product. This is a reaction. This is a substitution reaction. Okay, so that's reaction number 1. I'm not done with the question here. Reaction number 2. Reaction number 2 is like this. Reaction number 2. Four carbons and attached to the same leaving group. Okay, that's the leaving group. And it's reacting with, let's say, the same thing. You ignore the cation. This is the more important thing. The anion is the more important thing because that's your leaving group. Okay, and you make this product here. 1, 2, 3, 4 carbons. This is out. Chlorine is out. That's in. That's in. And this is the byproduct. So stare at the reactions for maybe 10 seconds. That's reaction number 1. Same nucleophile, different products, obviously. They look different. They're both ethers. They're called ethers. We haven't covered it yet. Okay. Okay. Ready? Review what we just did. Remember how I asked your questions, like the first page of the question, I'll be like, read the question carefully, review the reaction carefully, then answer the question. Review it. Okay. I'll help you with something else. I'll help you with something else. Alpha, beta, gamma. Alpha, beta, beta, beta. That's your alpha carbon that's connected directly to the leaving group. That's the happening place. This is important. So this carbon is important. This carbon is very important. That's your alpha carbon. Okay, ready? Done with your review? Okay. Somebody who has not answered today. So everybody who has answered, I'm banning you from answering. You're forbidden. You're going to be kept in a closed room with no windows and doors. Okay. Which of the 2 reactions is going to be Sn2 and which of the 2 reactions is going to be Sn1? Those of you who have spoken today, keep your mouth shut. Somebody else who hasn't spoken today, please unmute yourself, turn on your camera. I'll really appreciate that. Tell me which of the reactions is Sn2, which of the reactions is Sn1, and why. The hints are given on the right side, and we already talked about it. Somebody tell me. Actually, there is a song like that, very similar tune from the 80s. 80s or 70s. I'm an old man. Anybody? Okay, I'll give you a chance to the unusual suspects. So those of you who have spoken today, just stay quiet for another minute or so. Anybody who hasn't spoken today has any idea like which one is going to be SN2 and which one is going to be SN1? The secret lies in the alkyl halide, the nature of the alkyl halide. One of the alkyl halides is of one type and another alkyl halide is of another type. One likes to do something radical, other guy doesn't like to do that. One guy likes to be going through that process one step, one guy likes to go to an intermediate and go through two steps. Which one is which? Those of you who are kind of turned off your cameras and I don't know what you're doing behind the camera, hopefully not watching Netflix. Any idea? Anybody? Do yourself a favor, try to say something, please. Say anything, like it's a nice day. Or I'm sleepy, or I'm hungry. Say something, that will probably break the ice. Kevin? Your name popped up, maybe there was some noise.
Yeah, my mic's not working. I've been
Okay.
trying.
Anybody wants to pitch in and share some thoughts? Which reaction is going to be SN2 and which reaction is going to be SN1?
Number one's going to be SN2 and number two is going to be SN1.
Thank you, Trev. And this is Henry, or H is for, yeah, H is for Henry. Okay, so number one is going to be, Henry says this is going to be SN2 and this is going to be SN1. Why, Henry? Why would this be SN2 and why would this be SN1? What does SN1 produce? Give me that answer first. In SN1, something happens that doesn't happen in SN2. What happens in SN1? It's something funny, something reactive forms. What is that? It's 2 syllables. Well, more than 2 syllables. Something forms in SN2, SN1 that doesn't form in SN2. Anybody wants to say that? What forms in SN1?
I'll give it a try.
Yeah, Ray.
And the second one is the tertiary. So that's going to be
What will it like to form?
Carbocation.
Carbocation. So this guy is going to form a carbocation that looks like this. This guy, if it forms, if it could form, it would form a carbocation that looks like this. That's a primary carbocation, and this is a tertiary carbocation. Which carbocation is more stable? Marco or Ray? Either of you, or Henry?
Number
Which one is
2.
more stable?
That one.
Right?
Yeah.
Marco? Yeah. So this is stable. This is stable. Because each methyl group is pumping electrons into that direction. Watch the old videos or Google it. I don't Google it, watch our videos. Over here, the help is coming from only one. So this is a bad one. This is unstable. It won't happen. So if the carbocation doesn't happen, the reaction must happen like boom, boom, right? The nucleophile comes in, the living group leaves. It doesn't give the molecule a chance to form a carbocation. That means the answer from Henry was absolutely correct. This reaction is going to be SN2 and this reaction is going to be SN1. Perfect.
I got another comment on that. On the number one, it's easier for the paying guest to get in through through the alpha.
Ray, do you just realize that you just started speaking like a chemist? You are absolutely right. I didn't talk about it. I didn't introduce this concept. So what Ray is saying, I don't think this is going to be in the part of the important formal discussion. This is informal discussion, but I want to point out that what Ray is saying, that it's easier for the paying guest to get to the porch in the back from the back door. Because can you elaborate a little bit more, Ray? Why is it easier to access this alpha carbon here than this carbon here? Why?
Because it's a primary.
Primary
I
means
watched the video. The video was showing me that it's less, like you look at it, it's like less clutter. It's easier for the paying guest to get in.
absolutely. You deserve a bonus point. Absolutely. Absolutely. You're talking about what we talk about steric hindrance. Steric hindrance means crowdedness. This is, I didn't write it down, right? So this is actually a methyl group. This is a methyl group. This is a methyl group. Like each methyl group is like a little petal with 3 petals, right? Like a flower. So you got 3 of them stuck here, like 3 piece of a spaceship. 1, 2, and 3. And the alpha carbon is almost like buried in the center of the 3 petal stem of that flower or that plant. Over here, you got a flower with 2 hydrogens and a carbon. Yes, this is crowded, but these 2 guys are tiny. The hydrogens are tiny. So the crowdedness is much less there. So Ray is 100% correct. It's much more accessible for the paying guest, for the nucleophile. You're absolutely correct. And I really applaud your comment. You are talking like a chemist. Awesome. So it's much easier to access. Yes. And that lays the foundation for our next topic. What can go wrong in a substitution reaction? This is perfect. It just happened. I mean, there was a reason for Ray to mention that. So did everyone kind of get that? Why this is Sn2 and why this is Sn1? You can think primary and tertiary, and Dr. Maitra said tertiary is Sn1 and primary is Sn2. That's fine. If you memorize it, that's fine. Just get through this semester, pass, get a good grade. You know, I'm happy. Don't fail. Okay. It's the same nucleophile, same paying guest, different houses. One house more crowded in the back, one house more empty in the back, and so it happens, right? And everything kind of connects together. This carbocation sucks, this carbocation is awesome, so you can think about that way too. Either way works. Okay. I'm going to take a picture, and I'm going to use actually the same example and tell you like what can go wrong. And it may spill over a little bit into the next week discussion, but we will see. I don't want to talk about it anymore. Sn1, Sn2. Okay, we don't have much time today. So what I'm going to do is I'm going to erase. I'm going to use the same example. This is a fantastic example. Any questions? Quick questions about this, what we have discussed so far. So after this, we'll be left with carbonyl chemistry. And I think in 3 classes, I'm going to keep that quiz number 3 very, very simple. Like maybe 5 questions. I'm going to give you 10 minutes and maybe 15 minutes, 5 minutes extra after the class. So we're going to lecture almost for like more than an hour on Tuesday of 1 week from last Tuesday, okay, on 4th of May. I'm going to keep the quiz very simple so that everybody gets 100%. All right, I'm going to erase and redraw the molecule so that it's clean. Okay, so what can go wrong in an a substitution reaction? Okay. I'll just introduce it, and maybe we will have that question as bonus question in the final. So we're just going to introduce you to that and kind of have some tough questions in the final from that territory. Okay. I'm going to start using the roles in such a way so that they both look the same. They look like twin brothers or twin sisters. So I'm going to try to balance it out so that it's kind of like rotating the tires, front and rear. Okay, so this is exciting. I think this is really exciting. We have 5 minutes. And we can I just want to introduce the concept. Okay. Same starting compounds. I'm just going to use a different color. A red color, okay, that. And it's reacting with, I'm not going to draw the arrow. Let's just draw that nucleophile. This is your nucleophile. Okay, ethoxide. And on the right side, we have that and the nucleophile. Okay, and I totally get it, right? It's difficult for it to get in here, right? So what it likes to do is it likes to first detach itself and form this guy. Carbocation. Okay, I'm just going to draw this so that you guys remember what's going on here. Happy carbocation, that's why it happens. Plus Cl minus, and then this guy comes in. And it produces the chicken foot ether. That's the product. I'm not going to draw the CH3s again. You get the point. Over here, it cannot form the carbocation. We already talked about it. So what happens instead is it attacks from the backside, it kicks it out, and it produces this. Okay, one step. Step one. This is step one and step two. Okay, this is Sn1. This is Sn2. We don't have much time right now. Remember what Ray said just a few seconds ago, a few minutes ago. Ray said that this place is very crowded. When this place is very crowded, when the alpha carbon, the important carbon, when the alpha carbon is very crowded, you can see it's how crowded it is. 3 flowers stuck there, so the bee cannot get in there, okay? it's hard for the bee to get in. This is the bee, and it's like trying to get in there and drop like a little petal, right? So it's trying to get in here. It's easier for it to get in here. It's not so crowded. It's very crowded. Sometimes the nucleophile doesn't behave like a nucleophile, and the SN reaction gets completely screwed up. Okay. Instead of this guy behaving here, it's behaving like a nucleophile. Acting like a nucleophile. Here it's acting like a nucleophile. Okay, they're all acting like a nucleophile. Sometimes when it's very crowded and when the nucleophile is a very itchy reactive nucleophile like this dude, it does something else instead. So it looks for a low-hanging fruit. It doesn't like to do that hard job. It does something completely different. You know what it does? Instead of attacking the alpha carbon, it looks for a beta hydrogen. So this is an alpha carbon, just hanging there for like one or two more minutes. This is a beta carbon and beta carbon. This is a beta hydrogen. It looks for a beta hydrogen, and it takes care of its itch, the negative charge itch. Instead of attacking an alpha carbon, it plucks a beta proton, beta hydrogen. So what it does is it does something very sleazy. It attacks a beta hydrogen, grabs that, and this bond falls down here. Okay, this is a beta hydrogen. So when it attacks a beta hydrogen, what happens? Beta hydrogen plucked by this guy. So this guy is not acting like a nucleophile anymore. This guy acted like a base. What does a base do? Bases react with protons. A base's job is to pluck a proton. So it's got plucked by this. So now acted like a base because it's feeling lazy. It just doesn't want to get in here. Doesn't want to get in here and attack. It rather plucks a low-hanging fruit. That's the low-hanging fruit. So what does the product look like? Well, the product looks completely different. CH3, the carbocation was gone. You formed an alkene. Siren. Okay, this is an alkene. So when the nucleophile does not act like a nucleophile, but it acts like a base and grabs a beta hydrogen and dumping this bond, the two electrons in this bond in between alpha and beta carbons and forms a double bond, then this reaction is called an elimination reaction. Can you mute yourself, please? I don't know who that person is. Someone is.
I got a question, Dr. Mitra.
Yeah.
It's no longer a negative, right? Once you do that.
No, once you do that, it's not negative because now this guy was lacking an electron. It got an electron from that bond. We will discuss it a little bit on Tuesday. Don't worry about it. I'm going to just talk about elimination reaction for 15 minutes or half an hour, then switch to carbonyl chemistry. Sounds good? So I just wanted to kind of get the ball rolling, introduce you to the elimination reactions, and then we'll go from there. All right. Have a good weekend. Let me know if you want to sit down for office hours, but thank you very much for all your participation and your interest in the class. Almost done. Stay focused. As I said, I will do something about the second test. One quiz, though your worst quiz will be dropped. second test, we'll figure something out. I'll make sure that your bad grade or worst grade doesn't come in the way if you do well in the final. So stay motivated, do well in the final. Okay. All right. Take care, guys. Bye.
Thank you.
Yeah, no problem.